Yes, then various devices. Various devices. These materials are often developed through advances in material science, physics, and chemistry. Chemistry and including areas of photovoltaic, energy storage, and thermoelectrics. This energy efficient lighting also. Thermoelectrics, Rambabu is going to talk after me. He is theoretical. So these are the applications of emerging materials. These are advanced materials. So they are used in energy storage, energy conversion, energy harvesting, and hydrogen storage also. Most of Yassi Singh and other people are working in this field, senior Yassi Singh. So these are the definitions for students actually. What is battery? Then we have primary batteries, secondary batteries, then cathode and anode. Everyone knows it, chemistry people. So this is also when we are using, then we will go for a number of times this active mass, then this electrolytes, separators, fuel cells, electrochemical capacitors, ultra capacitors, and EDCL that I will introduce later on. Then this is a term used open circuit voltage when we are going to fabricate a device and characterize that device. So these terms are coming closed circuits voltage, the internal resistance, Faraday constant that is used for number calculation, thermal runaway when it goes to a particular stage. So electrochemical conversion devices are pervasive in daily life. Batteries, fuel cells, supercapacitors belongs to the same family of energy conversion devices. They are all based on fundamentals of electrochemical, thermodynamics, and kinetics. More chemistry is all three are needed to service the wide energy requirements of various devices and systems. Then supercapacitors are considered as an alternative to batteries and fuel cell. So just charge storage ability of a supercapacitor mainly depends on a specific surface area, pore structure, electrical conductivity, and charge transfer capacity of electrode material, how this charge transfer takes place. The performance of supercapacitor depends on nature and microstructure of electrode material. Professor started talking about electrolytes. So he modified the electrolyte for supercapacitor applications. We are still working on electrode materials. So this is a diagram that is called the Ragon plot. So you can see these are the conventional capacitor. Capacitors, then we have fuel cells which has a specific energy very high, and conventional capacitors they have a specific power, that one is very high. So capacitors are, supercapacitors are in between these two devices. This is supercapacitor, then there are various types of supercapacitors, then components of supercapacitors, commercial supercapacitors, and applications of these superconductors. So this is three types of supercapacitors. First one is called as electric double layer capacitors, second one is pseudo capacitors, and hybrid is in between these two. Both mechanisms are used. So you can see बोर्ड पे नहीं आ रहा है लाइट देखो ऊपर इसमें आ रहा है बोर्ड पे नहीं आ रहा है ऐसा नहीं दिखेगी आएगी so this is first one is electric double layer capacitors. So you can see that at anode and cathode there is formation of double layer, and capacity of this one is increasing because of that these two layers. In case of this pseudo capacitors, there are this one is anode and cathode. So these cations are these solvent molecules. They form a group of material, and this will increase the capacity of capacitor. So and this one is hybrid. That one is mix of these two. So energy storage mechanism for these three devices in electric double layer capacitors, capacitance is originated from the accumulation of charges at the electrode. Both electrodes, electrode and electrolyte interface. Therefore, controlling the specific surface area and pore size and enhancing the electrical conductivity these are the methods for increasing the capacity of a supercapacitor. Then energy storage of this pseudo-capacitance is realized through the transferring this Faradic charge between the electrolyte and electrode due to reversible multi-electron redox Faradic reactions. Chemistry people, they are more knowledgeable than we in this case. Then this energy storage in this one realized with the electrolyte and electrode due to reversible multi-electron redox Faradic reactions, which generally exhibit the high specific capacitance and energy density compared to first one. This is for mechanism of how these charges are in second one. So if you see this supercapacitors, then this is battery and this one is fuel cell example. So if you see the value of this energy storage devices and energy density and power density, because these two terms are very important in case of supercapacitors. So if you take a film capacitor, then this value of energy density is 10 to the minus 2 to 10 to the minus 1 watt hour per kg. If you take capacitors, that is conventional capacitors, where there are two parallel plates and in between you have dielectric material, then this one is less than 0.1 watt hour. This unit is energy density watt hour per kg. Sometimes this is called as grammetric density also, because this depends on mass. And second one is called as volumetric. This depends on. So you can see in case of supercapacitor, this value is 10 to the minus 1 to 10 to the plus 3, and this power density is also very high. That is in between these two devices. So this is just a comparison between these devices. So this is the difference in mechanism, what I have told you, how these charges are stored. If you take charge storage mechanism, then this here it is electrostatic, means charges are attracted because of their opposite nature of charge. Then this double EDSE, this one is non-Faradic, and materials used for this electrode are activated carbon, graphene, reduced graphene, CNT, and carbon aerogels. Then in case of pseudocapacitor, we have reactions like redox reaction under potential deposition, intercalation, electrochemical. That charge storage mechanism is electrochemical. Then this is Faradic, and these are the materials which are used as a electrode in this. That is transition metal oxide, especially MnO2WO3. Then conducting polymers also used as a electrode. In case of hydrogen, that is a mix of both. So when you have a electrode material, so you have to characterize that one so that you can compare the properties with others. So there are electrochemical parameters which governs the performance of supercapacitor devices. One is cyclic voltammetry, CV. Then we have electrochemical impedance spectroscopy, and this galvanometric charge discharge cycle. These are the three parameters. So if you are going to prepare a synthesize a electrode material, then you have to go for these three properties at least, so that you can say how this material is. So this is cyclic voltammetry, CV. Chemistry, you have 2, 3 setup also, 2 or 3. So in this case, this is used for this number of parameters you can realize through this this CV measurement, cyclic voltammetry. Actually, in cyclic voltammetry, we are plotting current versus voltage, and that nature of that relation between these two, that will depict the type of this supercapacitor. So this is the equation is used for calculation of specific capacitance. Yeah, that one is farad per gram, and actually you plot IV curve. Then the area under the curve, that one is IDV. This K is scanning rate. Yeah, that is called as scan rate. That is millivolt per second, where m is mass of the active electrode, that is active mass. Then from this we can calculate the specific capacitance. Then this is the, for these three type of electrodes, if you have EDLC, first one, yeah, this one is for ideal actually, ideal supercapacitor, this one is for pseudo capacitors, and the last one is for non-ideal capacitors. So the second parameter that one used to characterize this electrode material, that is galvanostatic charge discharge cycle actually. So this is various, how much cycles that material can go for charging and discharging process, this is used for that one. Then this is the CV curve for IV current versus voltage. This is for different type of electrodes. You apply different type of electrodes, then you will get this type of curves. Then this is IV dependence. So that depends on, I have written this I is equal to A V power B. Value of V will differentiate between these three. So in first case, when you have EDLC, then this B is 1. B is 1. If value of V is approximately equal to 1, then that will be for this GCD, and third one is for battery type of materials. So this is the, now this is electrochemical impedance. We can find out from this one. So impedance means contribution of different parts, different circuit elements, that is resistance, capacitance, or inductor also, then we call it combination of the three is impedance. So in this material actually, when you are going to measure the property of this one, so suppose you are using electrode, then bulk property and grain. That can be, you can find out from this. This in physics, this is called as Cole plot. So from this one you can find out the contribution of bulk material, grain boundary, and grains. So this is an important technique to find out the resistance impedance of material. This is the equivalent circuit of this one for this particular case. So if you have a super capacitor, then components are separator, collector, electrodes, and electrolyte. So this one I have shown in figure. This is collector in those both sides, the collecting current. Then you have electrolyte, separator, and anion cations, they are moving through that one, and this red color is electrode. So this is just about, this is not so important. So if you go for electrode materials, then for electrode fabrication actually, so commonly used electrode materials are activated carbon, graphene, then carbon nanomaterials, conducting polymers, transition metal oxides. So in this category we are using actually perovskite and spinels as a electrode material for supercapacitor. So electrode materials are transition metal oxide based, perovskites and spinel materials having spinel structure, because it is very easy to fabricate these materials. So these materials we are using to improve the property of supercapacitor. So this is again supercapacitor, different type of electrodes and their actual comparison. So this supercapacitor, we use this structure, compositional flexibility, and inherent oxygen vacancy. Perovskite structures have attracted wide attention for the promising electrode materials. These are the property of perovskite materials. And perovskite materials means formula is ABO3, where A and B are cations and O is oxygen. I will give you later on this structure. So in this perovskite structure, that ABO3 structure, you can have different type of doping to improve the property of that materials. Then you have this double perovskites, you have this iron non-stoichiometric compounds, you have. These are the different form of perovskites which we can play with different doping processing parameters. this is perovskite materials. They have different uses in different fields. That is the summary of that one. Then this is perovskite structure, that doping, non-stoichiometry, composite with other materials, morphology, synthesis. These are the parameters which controls the property of these electrode materials. This is again one type of nanomaterials. So challenges and towards the electrochemical supercapacitors. These are some important advantages of this supercapacitor, and which is more favorable comparison to other electrodes. These already students know that top to bottom and bottom top. These are methods for synthesis of nanomaterials. So, in case of supercapacitors, this power density indicates how fast a device can deliver the energy. Whatever energy is stored, how fast you can deliver that energy, that is governed by power density of supercapacitor. Then whereas you have energy density, that indicates how long an energy storage device can be used. That is the life of that one. So supercapacitors can outperform batteries in specific energy density and power density by many orders of magnitude. I have shown in Ragon plot. So these materials are versatile energy storage material. So before that, there are a number of methods for synthesis of ferrites. We have used with this Nilan Sahu is my MSc students. He used a green method to synthesize these ferrites. So this presentation is like the state of art of energy storage technology and all these things. So this is about perovskite structure. I have told you the structure is ABO3, X actually. So perovskites are also used for in solar cell material and other applications. Then ferrites, that one is similar to that is perovskites, but this formula is AB2O4, where V is iron Fe3+. So in the case of spinels, actually, these materials are oxide materials, so they have very high resistance. And in this case, if you take 1 unit cell, then there are 8 molecules. Total, you have 56 ions in 1 unit cell. Out of that, 32 oxygen. They are closely packed oxygen atoms. And in that cubic structure, you have 64 tetrahedral sites and 32 octahedral sites. Octahedral wide size is comparatively more than tetrahedral site. So these two cations in spinel structure, A and B. B is iron actually, Fe3+, and A is divalent. So if these divalent ions, if they are going to tetrahedral site, and this trivalent ions, they are going to octahedral site, then that one is called as normal spinel. But if divalent ions going to octahedral site, and half of the trivalent ions, they are coming to this tetrahedral site, then that one is called as inverse spinel. So these spinels are important, but generally people are using mixed one, means normal and inverse spinel. So these physical properties are interest to material science among the perovskites, including superconductor. These are the different uses. When they are used in solar cell, in efficiency you have get that in more than 26%. This is again about ferrites, what I have told you. A is divalent, that can be magnesium, manganese, cobalt, zinc, nickel, all these things. So by this green method, we have prepared this zinc cobaltite. This is a spinel material. So these are a number of advantages. So for this, we have used solution combustion method. In combustion method, there are different type of methods. So we have solution combustion method. So we have used in this case, this is called as green, because we have used the flower extract. This flower is available in our campus, that is called as Hindi Palas. And Palas, so we have collected that flower of Palas, then we have dried it outside for 1 or 2 days, then we have washed it, Then again we have dried it, and then we have taken this extract from that one. And that extract is used as a fuel. In combustion method, people are using a number of materials like urea and citric acid, all these things. So we have not used any of these things. We have used only extract of this flour. So that is why this is called as green method, and number of people are working on this one. So these are the how they have collected this flour extract, flour, and made their extract. So in this case, first we have collected flour, and after cleaning, we have prepared the extract from that flour, and using extract to synthesize zinc ferrite by Salgel method. So we have used that one in place of citric acid or in place of urea. So this is the Palas, is called as Palas flour, is already available in our campus. So we have collected from more than 3-4 kg of this one, and then we have dried it, then we have made the powder of that one, and for that powder, by boiling of some fixed time, we have taken the extract of that one. So in this case, he has collected 2.5 kg of flour, and then it was washed, and number of times dried and washed. Then we have made the powder of this one, and that from powder we have collected the extract. So this is the dry flour, and these are the powder of the flour. Then we have used in a beaker distilled water, double distilled water, and then the powder of that flour. And then we have used for at 18 degree for 1 hour. Then we have taken the extract of that one by filtering that one. We have used number of time filtering, so that extract is available, and that one we have kept in fridge. Whenever we are using, then we are taking it from fridge, not is at room temperature. So these are the different stages that students they have done. So this is the extract of flour. In this case, we have taken constituents in nitrate form, that is zinc nitrate, then cobalt nitrate in stoichiometric ratio, so that we can get exact spinel by using weighing machine. Then this one kept at 50 degree, and after 42 minutes approximately, we have calculated this one, how long we can keep it. So after this you can see, this is the doing process of this synthesis by using combustion method. So there is internal energy, by that this will come as a soft mass, and then we powdered it, and this one is now the material that is ferrite. So this is the powder form of ferrite. So based on this one, actually I have not used this one. There was a separate story for that one. We have not measured that one. So in another system, that is zinc ferrite doped with lanthanum. This one we have used as an electrode. So this one we have prepared. That is my research scholar Apurva Rai. She prepared, and this is published in Energy Storage 2-3 months back. So these are the XRD pattern. You can say this is very clean and metal is found. This is the ritual analysis that we have predicted the structure, and these are the parameters, because this lanthanum is substituted at iron oxide, ferric side. Then these are the different composition depending on the value of L, and then we have calculated lattice parameter. Then using Debye-Serre method, we have calculated the particle size. Then we have used Williamson-Hall method to find out the strain and particle size. Then we have also used calculated this X-ray density, and these are the hopping length. This is not used in this one. So these are the different ritual parameters for these 4 samples. This one is distribution of particle size. This is the TM image of that powder. And these are the CV curves, which I have told you that in ideal case you will get a rectangular type. So we have obtained this type of for different compositions. They have almost similar behavior. And then we have compared this value with other published research work, and we have found that our value is almost comparable to the reported values, yes, and better than some of the reported values. This is the scan rate versus specific capacitance, how it is varying, because this is important for application point of view. And this is the equivalent circuit. So from this work actually, we have, for this paperwork, we have synthesized material by auto combustion synthesis, where successfully synthesized pure and lanthanum doped. This is not doped, actually substituted, but in chemistry pool they are using doped. So this is lanthanum doped zinc ferrite for application as electrode material in supercapacitors. The detailed analysis confirms the formation of cubic structure without any secondary phase, because the XRD pattern was very clean. The incorporation of lanthanum into zinc ferrite enhances the electrochemical performance and capacitance when utilized as a supercapacitor electrode. We have used electrolyte, that is KOH. So lanthanum doped electrodes exhibit superior electrochemical properties, and finding this suggests that this lanthanum doped zinc ferrite holds promise as a high performance supercapacitor electrode materials. Now we are working on a series of this type of materials, where we have doped with different type of rare earth materials, and now we are comparing the value of this performance, how this is only better than others. So thank you all. Thank you all for coming. These 4 years of our vice chancellor. So university has developed like anything. We have gone from B+ to A++, and number 1 is UGC listing, where we can start our own courses without any permission from other agencies. So thank you all.
Thank you, sir, for a nice lecture. Now session is open for discussion. If you have any query, please ask.
यहाँ नहीं पूछ सकते तो बाहर पूछ लेना लेकिन पूछना जरूर. ये बहुत इंटरेस्टिंग है. You can take every type of flowers and you can synthesize these ferrites.
Anyone have any question? If there is no any question, then can calculate. Right now?
अच्छा है. Green, because we are not using chemicals and other things. No chemicals. No chemicals. We are using some chemicals, but we are not using harmful chemicals. For that, we have used this extract of this flower. The number of properties will improve when you use this green synthesis. Particle size, distribution of particle size, uniform. And XRD is also very good. If you use citric acid, then the XRD, there are number of small this impurity peaks are also there. In case of lanthanum doped, I have plus and 3-4 other flowers also. I will tell you, then other people will start in that one. So once it is, it depends on type of flower also. But this one is very concentrated, so we have used very small amount. That it is not that this much amount we have used and we have got it. We have varied this volume of this extract. Then we have seen the process and which one is the best. That one we have reported. Particle size is less than 100 nanometer. The same, we have not gone for same, but most of the particles are spherical. I have shown you the TEM image. Thank you, thank you.
Thank you, sir.
हैं? अरे मेरा मीटिंग है वहाँ.
अब 1 घंटा बोला, मुझे 1.5 घंटा करके कहाँ से दे?
तो बोल सकते हैं.
कहाँ है स्लाइड्स कहाँ? Thank you.
Dr. Ram Babu did his MSc
Thank you,
from
sir.
University of Hyderabad and MTech from IT Delhi.
Thank you.
Then he completed his PhD
अच्छा,
from IT Hyderabad.
point. So ये up है ना, up है ना?
Dr. Ram Babu has published more than 23 papers in national and
Thank you.
international reputed journals. His research interest is spintronic material, magnetism, topological materials, thermoelectric materials, and superconductivity by using density functional theory simulation. Okay, sir, please I would like to invite Dr. Ram Babu.
Thank you, sir, for the nice introduction. Can you hear me? Okay. So firstly, I thank the organizers for giving me this opportunity. So I am going to present study of the thermoelectric transport properties of gentle phase nitride Ca2Zn2, a first principles approach. So I want to know how many of you are familiar with simulations in this class? Okay, one person. Any simulations, molecular dynamics or density functional theory? Okay, so yeah. So the outline of my talk goes like this. In the first part, I will discuss the brief introduction about the density functional theory, and in the second part, I will discuss some of the results that I have obtained for this compound Ca2Zn2. So firstly, I will talk about why simulations are necessary. Then I talk what is quantum many-body problem. Then what are the problems associated with many-body problem. Then I go to Born-Oppenheimer approximation, and what is that approximation. Then what are the shortcomings in the Born-Oppenheimer approximation. Then what is Hartree method and its limitations. Then what is Hartree-Fock method and what are the limitations of the Hartree-Fock method, what are the complications involved. Then I will go to density functional theory, a brief introduction to the density functional theory, how it is overcoming the difficulties of the previous methods compared to the present method. Then I will talk about Kohn-Sham equation, some LDA GGA methods. Then I will discuss the results. So why simulations are necessary? Many times we are doing experiments, some people are doing theory and some people are doing simulation. So what is the correlation between theory, simulations and experiments? Suppose we are doing some experiment and we got you are expecting some physical properties or some chemical properties, and after measuring you are not getting the desired properties. The quality of the properties may be low, we don't know exactly. By using simulations, we can predict in advance how much gain or whatever, any physical property, how much we are going to get, that we can predict through the first principles calculations. Then we can compare it with the experiments also. We can do other way around also. First we can do experiment and we can try to prove it with the simulation, or first we can do simulation and we can say that yeah, this compound is going to have this much, some parameters, some properties, so we can go for the experiment. That also we can do. So in that case we have to do simulation, and many times what we do, suppose we do some experiment and the experiment involves costly chemicals, and after preparing the sample, what we do, we will measure and you are not getting the desired property, then the sample is a whole waste. So in advance what we can do, we can predict physical properties or chemical property, anything, any property, whatever we are measuring with experiments, that can be done with simulation. So we can do simulations and we can tell that yeah, you are going to get this nice property, so we can go with the experiments. That also can be done. So as I told you, there are different ways to study the condensed matter. One is computation, one is experiment, and another one is theory. So we have all correlations among these three. So now I come to many body problem. So what is many body problem? We know Schrodinger equation. Schrodinger has given this time dependent and independent Schrodinger equation in 1925, and which gives us H psi equal to E psi. What is H? H is the Hamiltonian of the system, which is nothing but kinetic energy plus potential energy. And yeah, it is not coming here. Yeah. Okay. So here we need to know the Hamiltonian of the system. Once if you know the Hamiltonian, you can substitute that Hamiltonian back into the Schrodinger equation and you can solve it. And is it true in all cases? Can we solve the Schrodinger equation for all cases? That we have to think. Yeah. So if you go to many body problem, suppose I am talking about one electron system. So what is one electron system? We know. In hydrogen, how many electrons are there? One electron is there. So for one electron, when you try to solve the hydrogen atom, by hand also we have solved in gradation. So if you solve hydrogen atom for one, hydrogen atom means it is having only one electron. So for one electron, how many variables we are getting? We are going to solve that hydrogen atom problem by using Schrodinger equation by variable separable method, where we have taken the total wave function as the product of R into some YLM theta phi. So R theta phi we have taken, right? So we have three variables, radial part and theta and phi. So you need to solve for three variables for one electron system. Then we have done some derivation, and after 20 to 30 pages derivation, we are using many approximations. There we some legendary polynomials, associated legendary polynomials, associated log array polynomials are also associated with that. And after doing some 20-30 page derivation, we are getting some ground state wave function in terms of theta, YLM theta phi into some R part, right? So this is applicable for one hydrogen atom system. But what if we go to more than one electron systems? Can we apply the Schrodinger equation to solve for more than one electron system? For example, if you go to helium is having 2 electrons in its atom, right? So for 2 electrons, how many variables are required? For 1 electron, we need 3 variables, right? For helium, 2 electrons, we need 6 variables. And if you try to solve by hand, theoretically, you cannot solve. Some people might have reported, but people don't believe that, right? So for 6 variables, second order differential equation, which is Schrodinger equation, is second order differential equation. Solving is very difficult. You keep on solving, you never get the solution. So fortunately, we have Schrodinger equation. On the other hand, unfortunately, we cannot solve it for 2 electrons. 1 electron we have solved, but for 2 electrons, we have the equation, we have second order differential equation, but we cannot solve. So what to do? So this is about 2 electrons, but in real life, we are dealing with real systems. Suppose somebody is working on zinc oxide, somebody is working on LiMnO3, somebody is working on some big molecules where this molecule is having 100 electrons. If you are having 100 electrons, 100 into 3, how many variables are coming? So can you solve it? It is impossible. Nobody can solve. So such kind of problem is known as many body problem. So there is a problem, right? So many body problem, many body means there are many electrons present in the system. So that is what I have written here. So for many body system, suppose I am having m number of nuclei and n number of electrons. So in that case, I have to find the Hamiltonian. As I told you, H psi equal to E psi is the Schrodinger equation, where H is kinetic energy part, and all these 3 terms are interaction terms, which are known as potential energy terms. So for n number of electrons, I can write this one as, this is sum of the kinetic nuclear kinetic energy, electron kinetic energy, and this is the electron nuclear interaction, electron interaction, and this is nuclear interaction. So the same I am writing here. The total Hamiltonian is nuclear kinetic energy, electron kinetic energy, electron nuclear interaction, electron interaction, and this one is nuclear interaction. So this is the Hamiltonian. Once if you know the Hamiltonian, you may substitute that into the Schrodinger equation and you will get the solution. But we are not getting the solution, unfortunately, for many body system. So such kind of problem is known as many body problem, because we are getting, for n electrons, we are getting 3n variables. So we cannot solve 3n variables. Okay? So let us try to understand the difficulty that is associated with many body problem. So what is the difficulty? I will take one example. I will take benzene as an example. So benzene is given by chemical formula C6H6. So in C6H6, we have how many number of electrons? We have C6, 6 into 6, 6 into 36. So 1 into 6, 6, 36 plus 6, 42 number of electrons are there in this system. Okay, so we have 42 number of electrons in benzene system. So I want to solve this benzene ground state wave function or ground state energy by using the many body problem or Schrodinger equation. So is it possible? It may be possible if you use the variational principle. So, variational principle we have to use. By using the variational principle, you can solve the ground state wave function of the benzene. So, how to do that? Let us try to see. So, as I already told, since we have 42 number of electrons, for 42 number of electrons, how many coordinates are coming? How many variables are coming? 3n, 3 into n. So, 3 into 32, 3 into 42, 126 coordinate Cartesian that equations are coming. So, can we solve it by hand? We cannot solve it by hand. So, let us try to use this one by using variational principle. So, for that purpose what I do, I take a cubic box of 10 angstroms and I will keep this benzene molecule into the cubic box, and in all 3 directions I will take for the discretization I take 50 points in the Cartesian space, 50, 50 and 50 in 3 dimensions. So, if I take like that, okay, so how many operations I need? I need m power 3n. M power 3n operations are required for one iteration. So, m power 3n means I have taken 50 points in all 3 directions. So, 50 power 3n, 50 power 126 operations are required for the matrix diagonalization in real space. Okay. So, if you want to minimize by using the variational principle, you have to find this energy. You have to minimize, if you want to minimize this one, for one iteration you need 50 power 126 operation, but within one iteration you are not going to get the ground state. You need several such iterations, and for each iteration you need 50 power 126 operations. Okay. So, for example, what I assume, I have a fastest computer with me, and that supercomputer, it can perform 10 power 18 operations per second. That is, I am assuming. So, my supercomputer is going to perform 10 power 18 operations per second. I am assuming that I have that supercomputer. So, now I want to solve this matrix diagonalization using variational principle, and I have submitted the job there in the supercomputer. So, is it going to, how much time it is going to take? Even the supercomputer with 10 power 18 operations per second, it cannot solve by using variation principle, it cannot give the ground state energy in our whole lifetime. Okay? So, you may get, but how many years? We do not know exactly, maybe my grandchild or my son may see. I may die, I will die after some time. Okay? So, in principle you can solve, but you cannot see that, and all the time it should be backed up. All the time we are having power fluctuation, 5 minutes power gone, we are going to switch off our computer. We have only 5 minutes time. Okay? So, all the time power should be supplied to the supercomputer, and that will perform operations, and that supercomputer is performing 10 power 18 operations per second, but I need for each iteration I need 50 power 126 operations, and several such iterations are required. So, ideally, though I can do it with variational principle, though I may get the ground state energy, but I cannot use variational principle for bigger system, because it takes more than a human lifespan, one human lifespan. So, yeah, so I cannot apply the variational principle. So, that is gone. So, now you understood the difficulty of the many body problem. So, we have discussed what is many body problem, 3n dimensional issue is there, and we try to solve it with variational principle. We could not solve by variation principle also, because it is taking years and years. Okay. So, to remove this difficulty of the 3n dimensional problem, people have come up with different approximations, and one such first approximation is Born-Oppenheimer approximation. So, in Born-Oppenheimer approximation, what these people have done, they have assumed the nuclei, they have not assumed, nucleus is heavy, we know, compared to the electrons, because nucleus is having protons, protons are having heavy mass compared to the electrons. So, what they assumed, nucleons are not moving compared to the electrons, because they are slowly moving, but they neglected that kinetic energy, their movement is 0. So, in that case what they have done, nuclei are stationary, so they are not moving, the kinetic energy of the nucleus is 0, and so if you make this one 0, now you can write the fresh Hamiltonian as this one, it is neglected, this is no more involved, it is there, and you can write the fresh Hamiltonian as only kinetic energy of the electrons, electron-electron interaction, and the other two interactions I am merging, and I am saying that that is external potential. So, now the Hamiltonian is transforming into this equation, and now once if I know the Hamiltonian, I can substitute back this one into the Schrodinger equation and I try to get the solution again. But if you see, though I have neglected two terms, one term I have neglected, kinetic energy I have neglected, but unfortunately the dimensionality problem has not gone. We have neglected one term, but still 3n dimensional problem is there, because if you have n electrons, you have 3n variables. So though Born-Oppenheimer, they have neglected this kinetic energy of the nuclei, but they could not reduce the dimensionality issues. So what they have taken, so they have assumed this, they are comparing this nuclei with elephant. Elephant is heavy and cannot move, but sometimes elephant they run faster than us. That is a different issue, but here I am showing that, and electron is like a freebie, so it will move faster. Okay, yeah. So Born-Oppenheimer approximation also we have dimensionality issue. Now come to Hartree method. So what is Hartree method? This is called n one particle approximation. Okay, so I have taken the quantum system. Now I need to find the ground state wave function for the whole quantum system, maybe zinc oxide or benzene, whatever. So what this Hartree has done, he has assumed the total wave function. Suppose in our hall we are having some 50 students, 50 electrons are there. Okay, so the total wave function of this whole system, this hall, is the product of individual wave function of each electron. So he has assumed the total wave function as product of individual wave function. So psi 1 into psi 2 into wave function of psi 3 into so on into psi 50. Okay. So he is assuming the total wave function of product of individual wave functions of the whole system. Okay, that is fine. He has assumed. Now he is assuming that this is the total wave function. Total wave function means when you substitute this wave function psi into the Schrodinger equation, h psi equal to E psi, it should get satisfied, because he is assuming that this is the total wave function. So what he has done, he has substituted this wave function back into the Schrodinger equation, and he ended up getting this Hamiltonian, kinetic energy plus potential energy part. He got this one, and the last term will tell you the Hartree potential. This is called Hartree potential. Okay, but is it the perfect method? Do we know? Can we claim it? Is it as a perfect method? No. Why? Because the total wave function, he is taking it as product of individual wave function, and if you see this total wave function, it is symmetric in nature. It is symmetric, but electrons are fermionic in nature, so they should satisfy antisymmetric property and should obey Pauli's exclusion principle. So this total wave function, it does not obey Pauli's exclusion principle, which is a limitation to this method. So unfortunately in Hartree method also we have some shortcoming. The total wave function is not antisymmetric because electrons are fermionic in nature, they should satisfy antisymmetric property, but the total wave function taken by Hartree is coming out to be symmetric. Okay, so that is one more shortcoming. So that is what I am writing here. It has not considered the antisymmetric nature of the wave function because electrons are fermionic in nature, and it is not obeying Pauli's exclusion principle. Okay, and the electrostatic interaction, it was treated in average manner because this is average approximation. Okay, and it also will not contain these exchange terms. So these are the shortcomings that are associated with Hartree approximation. Then we are coming to Hartree-Fock method. So in Hartree-Fock method, to avoid this symmetric nature of the wave function, Hartree and Fock, they came up with some other approximation. So they have used the Slater determinant to get the total wave function of the system. Okay, so this is the Slater determinant. So in Slater determinant they have written like this, and this gives you the total wave function of the system. So now the total wave function of the system is given by, for n electrons, it is given in terms of Slater determinant. So for example, if I take 2 electrons, the Slater determinant will be 1 over root 2 factorial pi 1 r1 into pi 2 r2, pi 1 r2 into pi 2 r1 into pi 1 r2. So now this wave function will take care of the antisymmetric nature of the electrons, and it obeys the Pauli's exclusion principle. Okay, so in Hartree method, it is not obeying Pauli's exclusion principle, but here when you consider this Slater determinant, it is obeying the Pauli's exclusion principle because this wave function is now antisymmetric in nature. Okay, so once if you substitute this later determinant total wave function back into the Schrodinger equation and you try to obtain the total Hamiltonian of the system, it will give you all these terms, and this term is Hartree-Fock potential. This one is Hartree-Fock potential, this one. Okay, but there are some problems which are associated with Hartree-Fock method also. Here there is a lack of electron correlation. Electron correlation means, suppose in the system we have 50 electrons, the movement of one electron, how it affects the other electrons, it was not treated properly. Suppose I am one electron, I am moving through the solid, you are all other electrons. So my motion, how my motion affects the presence of the other electrons in the system was not told clearly by this Hartree-Fock method. So that is called lack of electron correlation. So electron correlated movement was not treated in this method. So this is one shortcoming, and similarly some other shortcomings are also there. It is not suitable for strongly correlated systems. Maybe for d orbital and f orbital system it is not applicable, and computationally it is expensive. Some people are doing in chemistry, they use this Hartree-Fock method, and it will take a lot of time. Even in WASP also it takes a lot of time. So it is computationally expensive, and overestimation of ionization energies and underestimation of electron affinities, all these are associated with this problem. Okay. So till now what we have seen what is many body problem, what are the problems associated with many body problem, then we came to Born-Oppenheimer approximation, neglected that kinetic energy of the nucleons, but unfortunately these two methods, they are having dimensionality issue, 3-dimensional problem is there. So we cannot solve Schrodinger equation. Now coming to Hartree and Hartree-Fock methods also, one method is having a symmetric wave function, and another method is not taking this correlation moment of the electrons properly. So now what I do, I go to density functional theory. So what is density functional theory? What is the need for the density functional theory? So when I was discussing about this many body problem, I have 3n variables. Okay. So suppose for example, if I transform these 3n variables into 3 variables, my life is easy, right? So so if I transform these 3n variables back into 3 variables, I can solve it, because we have done it for hydrogen atom also. So what I do, these 3n variables, I just want to transform into 3 variables, and I need some parameter which I can express in terms of 3 variables. Okay. So that is what I am exactly looking for, and it is given by electron density of the whole system. So the electron density can be expressed only in terms of spatial coordinates nx, ny and nz. So for this purpose, what Thomas and Fermi they have given in 1920, they have expressed kinetic energy in terms of electron density. I did not write here. Kinetic energy they have expressed in terms of electron density. So this whole DFT is dependent on two theorems, Hohenberg-Kohn theorems, and Hohenberg-Kohn theorem, first one will tell you the ground state energy of is a unique functional of the electron density. So you can express ground state energy in terms of the electron density. And the second Hohenberg-Kohn theorem, it states that the electron density that minimizes the energy, because we need ground state energy, minimum ground state energy, the electron density that minimizes the energy is the true electron density. Okay. So you are feeding the electron density to get the minimum of the energy, and you get the minimum energy and corresponding that electron density. Okay. Electron density that minimizes the energy is the true density. So by playing with the electron density, I will get the ground state energy. Okay. And I know ground state energy is unique functional of the electron density. So my aim is to find out the electron density that gives the minimum energy. If it gives the minimum energy, the corresponding electron density is the true electron density. Okay. So there is a proof for these two theorems which are not required here. So based on these two theorems, density functional theory is built. So by using these two theorems, Kohn and Sham, what they have done, they have modified this Schrodinger equation into Kohn-Sham equation. This is known as Kohn-Sham equation. Here the kinetic part is there, external part is there, right? Hartree, this this part is there, and this exchange correlational part is there, which is equal to this energy. Okay. So, here you can find out the energy, this ground state energy into this all these terms. Here everything we know, this is the external energy, this is the Hartree energy, this is the kinetic energy. The only term that we do not know is the exchange energy. Okay. So, all things we are doing in DFT is to find out the ground state energy. In ground state energy, all things can be known except this one, exchange correlation energy. So, what is exchange correlation energy? Exchange correlation energy I told you already. Correlation energy is correlated movement of one electron, the presence of one electron movement. Okay. How it affects the other electrons, nobody knows. And similarly, what is exchange energy? If you exchange two electrons in the system, how much energy it costs? But we have many electrons in the system. We are not talking about two. That also it is computationally expensive. Nobody knows. So, all terms we know except this exchange correlation energy, and this exchange correlation energy, people have given some exchange correlational functions which are known as LDA, GGA, HSE, and in Gaussian you say B3 leap, some sets are there, right? Basis sets, exactly. So, the self consistency loop for DFT I am giving like this. So, first I will give some input ground state energy that will be taken by the crystal structure itself. It will generate some energy, that electron density. So, what I do, I have to solve this Schrodinger equation. Schrodinger equation is H psi equal to E psi, H equal to kinetic energy plus potential energy. This energy in the form of electron density. Now, what I do, I will give some guess density, because this is generated already, and also I will set some energy convergence criteria. Cutoff energy I will give some 10 power minus 6 electron volts, or here it is giving how many? 1, 2, 3, 4, 5, 6, 10 power minus 6 electron volts. So, this density, initial density is supplied, electron density. This initial electron density we are going to keep here. So, you will solve it, you will get psi and epsilon, but whatever the density, fresh electron density, if it is less than the old density, then it will go here and it will give the fresh electron density again. So, these iterations will continue, but the moment when the updated density is equal to the old density, this will be stopped and it will give you the ground state energy. Okay. So, we will get ground state energy in terms of the electron density. So, this is called as self consistency loop, SCF calculation. So, these are the basics about the DFT. So, in DFT we have the self consistent field calculation, and as I told you already, we do not know exchange correlation energy exactly, right. So, in Kohn-Sham equation we are getting total energy in terms of the electron density E rho. In E rho every term we know except EXE, exchange correlation energy, and these exchange correlation energy functionals are given by different approximations. One first approximation is LDA, local density approximation. So, in local density approximation they have assumed that the density is varying linearly, very slowly with time. Okay, and for that they have given some expression, and you can use that expression and you can do the calculation, and that is called as LDA. So, we are doing DFT in LDA approximation. Similarly, but some of the problems are associated with the LDA. When you optimize the system, it give you the lattice constants which are less compared to the experimental lattice constant. So, to avoid that, people have come up with generalized gradient approximation. So, they have taken the gradients of the electron density also. In that case, some of the improvements can be made. Here you are getting the lattice constant may be overestimated compared to the experimental ones. So, here also it is having some kind of difficulty, but together LDA and GGA exchange correlational functionals will give you wrong band gaps. It will not give you exact band gaps. If you want to get exact band gaps, you have to use some other functionals which are called as hybrid functionals, HSE, MBJ, GW approximation, and meta GGA calculations you have to do. But all these hybrid functionals, they will cost you more. They are computationally expensive. If I use LDA and GGA, I may finish my calculation in 2-3 days. But if I use HSE and this meta GGA scan functional, it may take 3 months. So, once if you submit job on the computer, you have to wait for 3 months. You may get some wrong exact result, but computationally it is expensive. We have to wait. Yeah. Oh, how to make it full screen? No. Full screen is exited. Yeah, for his contributions to the density functional theory, Walter Kohn, he was awarded Nobel Prize in 1998 for the development of density functional theory. Okay, so he has developed this theory proof in 1964 and he got the Nobel Prize in 1998 in chemistry. So based on this density functional theory, I will try to discuss some of the results that I have obtained for my compound using density functional theory. So what I have done, I have calculated thermoelectric properties of the gentle phase compound Ca2Zn2. So since I am talking about the thermoelectricity, so we need to know some energy problems. So I will focus on energy materials, and we know that nowadays there is a great demand for the energy. Everywhere energy is needed. 10 years back, if you go villages, people were not using any AC, fridge, TVs, of course they were using. Okay. But nowadays, if you go to village, every home is having, of course one should have, every home is having AC, fridge, refrigerator, microwave, all those things are there. But they need electricity, energy. How to get that? If you go to Andhra Pradesh sometime back in 20 years back, we used to get only 2 hours current, 3 hours current, that to night time. Whole day we were waiting for current, no electricity. Okay. So there is a great demand for the energy, and all the time we are using mobiles, and these mobiles, many students what they do, whether they are talking or it is in charging mode. It is not means like they don't leave it as such. They are either talking or in charging mode. For that also you need energy, right? So I am sorry, So what are the current problems associated with the energy? We know increasing pollution. This increasing pollution will give you a lot of problems, greenhouse emission, all those things, right? We need to look for some other energy sources. Whatever the natural sources we have, gas, oil and coal, these are depleting day by day. And maybe after 50 and 100 years, this coal is not existing anymore. We are digging, nothing will come after some time. Because you have to allow some time, 2000, 3000, then only that will develop. Okay, we are digging, more than what is required. So, coal is gone after 100 years, no oil, no gas, nothing is there in the core of the earth. So, we need to look for some alternative solution, and that alternative energies that come with some alternative energy sources, and one such energy source is solar energy, wind energy, tidal energy. So, there are many energy sources, and one among them is thermoelectric energy. So, in thermoelectric energy, we can generate the electricity from the waste heat recovery. From waste heat, we can generate the electricity based on the Seebeck effect. So, I focus on this alternative energy, and of course, this workshop is also environmental nanotechnology. I am not doing nanotechnology, but I am doing some environmental friendly energy resource calculations. So, that is thermoelectric energy. So, which gives you the electricity from the waste heat. So, what is thermoelectricity? The materials which convert heat into electricity, they are known as thermoelectric materials, and they are based on Seebeck effect. In Seebeck effect, we have two junctions, hot and cold junctions, and due to the temperature gradient between these two hot and cold junctions, that will give you some voltage which is known as Seebeck voltage, and this effect is known as Seebeck effect. And we can find out the Seebeck coefficient S equal to minus delta V by delta T. Okay, so based on this, we can try to harvest some energy by using this alternative thermoelectric effect. So we have some applications on this thermoelectric materials. For example, if I take some people have means like some companies have already developed few applications, and one such one is Citizen Eco Drive Thermo Watch. So how it operates? It converts the temperature difference, because watch we are wearing, okay, so it is touched to hand. So it converts the temperature difference between body and the surrounding air. There is a difference, delta T. So, temperature difference between body and the surrounding air into electrical energy, and that is enough to run the watch. You don't need any particular battery, and here no battery is needed, and its operation time from full charge. After full charging, operation time is 6 months. That means approximately 16 months in power saving mode. Power saving mode में रखेंगे तो 16 months होगा, हम नहीं रखेंगे 6 months तक चलेंगे, ठीक है? Okay, so this is one application of the thermoelectricity. On the second application, in automobile applications we have this one. Or we are driving car, in car there is a lot of waste heat is generated. Suppose if you can use that waste heat to develop some thermoelectric device, a thermoelectric generator, that is beneficial and that will give you, that will save you some petrol, right? So here what this BMW company has done, it has manufactured this thermoelectric generator by using the waste heat generated inside the car. So what they are doing, waste heat generated in the car is converted to electrical energy, and this energy can be used into internal parts which increase the fuel efficiency. So this kind of thermoelectric generator you can see in BMW series 5 make model 2010. So it is attached with gasoline engine with thermoelectric generator. So in car we are getting waste heat and that is converted into, and we can have some other application also in defense applications. If you see soldiers, sometimes in news we watch, soldiers are carrying lot of weight, पीछे बहुत weight है, lot of weight they are carrying, and they are having some AK-47 gun, they are running. Sometimes they have to climb mountains also. So is it possible to carry some 20-30 kgs all the time? No. And they are carrying some electronic gadgets, and electronic gadgets they are having batteries, right? So what we try to do, we try to reduce the weight of the soldier by using this thermoelectric technology. So whatever the electronic gadgets or instruments they are carrying, if we are replacing them with thermoelectric technology, then we can reduce the weight of the soldier by almost 30%. So that way this thermoelectric technology can be used. So what it will do, it converts the temperature difference between the soldier's body and the surrounding into electric energy, and that may be used into some device which may be useful for the military applications. So this is also one such application using thermoelectric materials. Yeah, so we need to find the thermoelectric materials with high figure of merit. So what is figure of merit? Figure of merit is a dimensionless quantity which quantifies the whether this material is suitable for thermoelectricity or not. If you are getting high figure of merit ZT, then it is most suitable for the conversion efficiency is more from heat to electricity. So it is given by the formula ZT equal to S square sigma by total thermal conductivity Ke plus Kl, where Ke is the electronic part of the thermal conductivity, Kl is the lattice part of the thermal conductivity. S square sigma is known as the power factor, where capital S is given by the Seebeck coefficient. We have seen that already. Sigma is the electrical conductivity and T is the absolute temperature between hot and cold junctions. Okay. So by looking at this formula, we have in numerator S and sigma, and in the denominator we have Ke and Kl. So if denominator is less, Gt is more. If numerator is more, Gt is more. So our aim is to increase power factor S square sigma so that Gt is more, or otherwise our aim is to decrease the total thermal conductivity Ke plus Kl. Okay, so the good thermoelectric materials, they should possess high S so that Gt is high sigma so that the figure of merit is high, and low lattice part of the thermal conductivity. So we need to look for such materials where S is high, sigma is high, and lattice part of the thermal conductivity is less. So how to choose the materials? So what kind of materials I have to choose? So we have materials, metals, semiconductors and insulators. So if I am talking about metals, electrical conductivity is very high. We know copper wire is copper, aluminum, silver, all those wires are highly conducting, conductivity is very high. That's good. But unfortunately, if you come to Seebeck coefficient, because we need also high Seebeck coefficient for high figure of merit, it is very low. And thermal conductivity is also very high for metals. So metals are not suitable for thermoelectric applications, because if you see the figure of merit formula, S and sigma must be high, but sigma is high, S is very low, and K is also very high. K should be low. Our expectation is low. So metals are not suitable for thermoelectric application. When you come to insulators, conductivity, electrical conductivity is extremely low. They are insulators. So they are also not applicable. Seebeck coefficient is high, again this one is low, but this one is very low. So this is also not applicable. So now you come to semiconductors. Semiconductors, electrical conductivity is maybe moderate, but here you have high Seebeck coefficient and low thermal conductivity. These two parameters, they are deciding whether to choose semiconductors are suitable for thermoelectric applications or not. So we can say that semiconductors are a good platform to study the thermoelectric characteristics. Okay. So now we have decided among metals, semiconductors and insulators, semiconductors are the best material for which we can explore thermoelectric properties. So what I have done for my compound, I have used Vienna ab initio simulation package VASP for my electronic structure calculations. Then I have studied the vibrational properties by using PhonoP and Phono3 codes, and thermoelectric properties, they are explored by using AMSET code, and this AMSET code uses semi-classical Boltzmann transport theory. And thermal conductivity has been calculated using empirical Slacks model, and I have also used Phono3 code to obtain the thermal conductivity. So as I told you already, I have taken this gentle phase nitride Ca2ZnN2, and this is a periodic solid. It exists in the crystal structure, tetragonal crystal structure with space group 139, and the conventional cell is shown here. In the conventional cell, how many number of atoms we have? We have 2 calcium atoms, 2 zinc atoms, and 4 nitrogen atoms. So what I have done, I have optimized this conventional cell by using exchange correlation energy functionals PBE and PBE sol, both are GGA functionals, and after optimization I have seen that the volume of this PBE is coming close to the experimental one. So I have continued all my calculations with PBE exchange correlation functional. So once if I get the optimized conventional cell, I have converted into primitive cell, and this primitive cell is having 2 calcium. This is the primitive cell of the conventional cell. This primitive cell is having 2 calcium atoms, 1 zinc atom, and 2 nitrogen atoms respectively. And I have calculated all these calculations in reciprocal space in the first Brillouin zone, and the Brillouin zone high symmetry points are also shown here. So immediately after the optimization, I have to check for the stability. There are different types of stabilities are there: chemical stability, thermal stability, mechanical stability, dynamical stability. So I have checked few stabilities. The compound is whether mechanically stable or not, it can be ensured by a Born stability criteria, and for tetragonal structure, the Born stability criteria is given by these expressions, and from the obtained elastic constants, all these criteria are getting satisfied, implying that the compound is mechanically stable. And I can find out the Young's modulus E and bulk modulus B, I have calculated, and if you are having high Young's modulus and high bulk modulus, indicates that the compound is highly rigid and hard. And the calculated B by G ratio is 1.75, and sigma is greater, the Poisson ratio is sigma is greater than 0.26. If these two conditions are getting satisfied, the compound is ductile in nature, otherwise it is brittle. So here the studied compound is ductile since these conditions are satisfied. And Debye temperature is the characteristic temperature of a solid, which differentiates the high and low temperature regions of a solid, and we are getting the high Debye temperature for the studied compound, 418 Kelvin. So the compound is mechanically stable. Then I tried to study the dynamical stability by using the molecular dynamic simulation. What I have done, I have taken up to some time, I tried to calculate the root mean square displacement, and this root mean square displacement, it is almost stable over the studied time from 0 to 16 picoseconds, implying that the compound is at 500 Kelvin. So at 500 Kelvin up to some time, the compound is thermally stable, implying the thermal stability in this compound. Then I calculated phonon dispersion of the compound. The positive phonon frequencies will give you the dynamical stability in this compound, and the phonon DOS, from phonon DOS we can tell that in which region what type of atoms are contributing. And we know that the atoms with heavy mass, they will vibrate with low frequency. The atoms with light mass, they will oscillate with more frequency. And if you see here, we have only 3 atoms, calcium, zinc, and nitrogen. So nitrogen is light mass, so it oscillates with high frequency. If you see nitrogen, right? Similarly, zinc is, compared to these ones, zinc is heavy atom, so zinc is oscillating here, since it is having heavy mass. So what atoms contribute in the what region to the what kind of vibrational modes will be known by this phonon dispersion. Then I have calculated electronic structure of this atom. by electronic structure calculations you can find the nature of the band gap, nature of the chemical bonding, what kind of effective mass you can expect, all those things you can study through electronic structure. So electronic structure I have calculated by using PBE functional without spin orbit coupling and with spin orbit coupling along the high symmetry path, and you can see that the band gap is coming around here. So it is not a direct band gap because momentum vector is not converging here. So indirect band gap semiconductor having this much band gap, and this band gap without spin orbit coupling is coming out to be 0.74 electron volts. With spin orbit coupling it is coming out to be 0.73 electron volts. But both these band gaps, they are not matching with the experimental band gap. What is the experimental band gap? 1.62 electron volts. But if I want to get the correct thermoelectric properties, I have to match the calculated band gap exactly with the or nearly with the experimental band gap. So PBE and PBE without spin orbit and with spin orbit, they are not giving some fruitful band gaps. So what I have done, I have used some hybrid functional, MBJ functional I have used using WASP. This time I have calculated the band gap by doing the density of states calculation. If you see here, the total density of states, you can see that this is band gap here, this is valence band and conduction band, and here it is band gap, you can see this. So this band gap is coming out to be 1.67 electron volt, which is closely somewhat matching with the 1.62 electron volts experimental band gap. And you can see that from this graph, which orbitals of the which atom are contributing in which region. Calcium p orbitals are contributing which region, you can study by using the partial density of states, you can see from the figure. So later on what I have done Bader charge analysis for the studied compound. So I have calculated how much charge is flowing from which atom to which atom during the process of this crystal formation, and I concluded that I know the Pauling electronegativity values, we know from the periodic table. Pauling electronegativity values, calcium, zinc and nitrogen atoms are given by these values, and Pauling electronegativity is high for nitrogen, 3. Pauling electronegativity value is 3 for the nitrogen atom, and we know very well know that the elements with higher electronegativity, they will attract the charge from the lower electronegativity elements. Elements with higher electronegativity, they will attract the charge from the lower ones. So therefore, from that logic, nitrogen should attract charge from calcium and zinc. And how to confirm that? So Bader charge is giving that, and we can check the same from the charge density plot. So what I have done, I have plotted charge density along 1, 0, 0 plane. In this plane all atoms are covered. So we can see that since it is having high electronegativity, the elements calcium and zinc are having low electronegativity values. So nitrogen attracts charge from calcium and zinc atoms, that can be seen from here, and the amount of charge how much is transferred I have written here. The Bader charge on calcium, zinc and nitrogen are 1.41 electrons, 0.48 electrons respectively, and these are losing charge and are accepted by nitrogen atom because it is having 1.6 electrons. Okay. So nitrogen is having higher electronegativity value which attracts the charge from the lower ones, calcium and zinc. So this is the Bader charge of this one. So in order to predict the accurate thermoelectric properties, we need to estimate the carrier lifetime. If you want to estimate the carrier lifetime, you have to go, you have to find the scattering rates of the lifetime carriers, maybe p-type carriers or n-type carriers we have to find. So the scattering rates are approximated by using Fermi's golden rule, where it is given by this formula, where this G and M is given by electron phonon coupling element, and this electron phonon coupling element is different for different scattering mechanisms. There are 3 scattering different mechanisms that I have studied. One such scattering mechanism is acoustic deformation potential scattering, ADP, ionized impurity scattering, IMP, polar optical phonon scattering, POP, ADP, IMP, POP. And this ADP is due to the interaction of the electrons with acoustic phonons, and ADP dominates at low energies and low temperatures. Its scattering rate is proportional to T into energy. It is basically elastic in nature. Similarly, when it comes to ionized impurity scattering, it is due to the Coulomb interaction between the charge carriers, maybe p-type or n-type, and charged particles. And it is significant at low temperatures and high doping. And scattering rate decreases with higher carrier energy. And it is also elastic in nature. Both are elastic in nature. And when it comes to polar optical phonon scattering, POP scattering, it is caused by interaction with the longitudinal optical phonons in polar material, and it is important in polar semiconductors and at high temperature, and it strongly affects the mobility and the electrical conductivity. It is inelastic in nature. So these three scattering mechanisms I have studied, and I found the scattering rates and hence carrier lifetimes. So for all these three scattering types, I have given this electron phonon coupling matrices, and for my compound I have studied these two are for n type. N type means electron concentration is n type, and this is for p type carriers at 10 power 19, 10 power 20, 10 power 19 and 10 power 20. So up to 500, 100 to 500 temperature by varying that I have studied, and for all the cases the scattering is increasing with temperature, and you can see that the scattering rate is mainly due to the pop scattering, POP. So why is it so? Because the pop scattering is governed by the difference between the static dielectric constant and high frequency dielectric constant. I have calculated static and high frequency dielectric constants, and the difference is coming more. If the difference is more, then we can say that it is due to the polar optical phonon. So from this logic, we can say that the pop scattering among the three studied scatterings, pop is more dominant compared to other two scattering for both n-type carriers and p-type carriers. So once if you know the scattering rate, inverse of the scattering rate will give you lifetime. So we can find the carrier lifetime for two concentrations for both n-type and p-types. So we can see that as a function of temperature, the carrier lifetime is decreasing monotonically. Why it is decreasing? If you increase the temperature, there is more phonon activity. Due to that one, scattering rate is more. If the scattering rate is more, lifetime is less. And you can see that for both type of carriers, it is decreasing. So now I know carrier lifetime, and this carrier lifetime is used to calculate the thermoelectric property. Then I have estimated lattice thermal conductivity by using the Slack's model, which is purely empirical model. So in Slack's model, it depends on this Grunesian parameter which gives you the anharmonicity in the crystal, and this is absolute temperature, and theta d is the I found that Debye temperature. So I know Debye temperature, and all these parameters I know, and I can find the lattice thermal conductivity as a function of temperature. And also I have used phono 3 pi, which relatively gives more accurate thermal conductivity. So I can get the thermal conductivity tensor here. So by using these two methods, I have calculated the lattice thermal conductivity as a function of temperature, and for both models, the trend is same, but it is decreasing. So it is quickly decreasing up to 200, then it is decreasing slowly, and the higher value of gamma means Grunesian parameters, which tells you the anharmonicity, and low theta d, it will give you the, it may give you the low KL values, but since we have here theta d is more, so we may expect higher thermal conductivity values, which are not good for high figure of merit. But unfortunately for this compound, we are getting high theta d value and higher anharmonicity gamma value, so it may give you some high thermal conductivity, which is not desirable, because generally ultra low thermal conductivity is expected. Maybe sometimes it may be less than 2, but here it is starting at 45, which is not desirable. So what we have done, we tried to calculate the mobility also for p-type and n-type for different concentration dopings. So we can see that the mobility is higher for whole type doping, indicating that p-type nature of the compound. It is p-type, because for p-type the mobility is more, so indicating that it is p-type in nature. Then we have calculated electrical conductivity also as a function of carrier concentration, and also as a function of temperature for different dopings, as a function of carrier concentration for different temperatures, and up to 10 power 19 there is no significant increase in the electrical conductivity, and after that it is increasing, and you can see that the electrical conductivity for p-type doping is more compared to the n-type doping. The dashed ones are p-type dopings, and it is consistent with mobility values, because for mobility also p-type is more. Mobility values are also more for p-type, and therefore the conductivity is also more for p-type here. And also we can see that the electrical conductivity for both cases, for both doping, it is decreasing with temperature. Okay, because if you increase the temperature, it increases the lattice vibrations. At the higher temperature, due to the increased lattice vibrations, it will enhance the phonon scattering, so that gives rise to the decrease in the electrical conductivity of the material. Similarly, what I have done, I have calculated the electronic part of the thermal conductivity. For semiconductors, lattice part of the thermal conductivity plays a important role, but we can find out electrical conductivity also. So, with carrier concentration, up to here there is no negligible increment, but after 10 power 19 to 21 there is a significant increase in the thermal conductivity with the concentration. And also, if you increase the temperature, the thermal lattice part, electronic part of the thermal conductivity decreases. Okay. So, why it is decreasing? Due to the increasing electron phonon interactions. And another important parameter is Seebeck coefficient, which is placed in the numerator part of the figure of merit. So, we can see that with carrier concentration, the Seebeck coefficient is decreasing. It is decreasing with carrier concentration, but with temperature, the Seebeck coefficient is increasing. And you can see that for n-type, Seebeck coefficient is more. For n-type, Seebeck coefficient is more, but for p-type, conductivity is more. So, finally, you may get a high GT for p-type materials. So, here for n-type, Seebeck coefficient is more, and here we have given the reason. It increases with temperature for both n-type, p-type carriers, and but for n-type, S is more. Okay. And what is the reason for higher S value? It may be due to the higher density of states, or due to the effective mass. Effective mass is coming from the band structure characteristics. Okay. So, if you have a parabolic thing, if you have a flat band, you have heavy effective mass, heavy holes or heavy electrons. If you have parabolic, you have lower effective mass. Then coming to power factor. So, power factor is also an important parameter, which tells you the how much amount can be converted from heat to electricity, So, we have found the power factor as a function of carrier concentration for different temperatures and as a function of temperature for different dopings. And you can see that the carrier concentration is from 10 power 18 I have taken, it is increasing up to some extent here, and after that for one point it is decreasing. And similarly, here also you can see that initially it is decreasing with increasing temperature, okay, due to the phonon scattering at enhanced temperature, elevated temperatures. But though the n-type carriers, they are exhibiting high Seebeck coefficient. If you go back, n-type carriers are having high Seebeck coefficient, but power factor is slightly higher for p-type carriers. Power factor is slightly higher for p-type carriers, as can be seen from the graph. So, once if I know the power factor S square sigma I know, Ke plus Kl I know, for different concentrations I know, for different temperatures also I know. So, once if I know the power factor for different concentrations and different temperature, and I can plot figure of merit as a function of carrier concentration and as a function of the temperature. Okay. So, here you can see that the figure of merit is increasing with carrier concentration for different temperatures, and at the same time this one also, it is also increasing with as a function of temperature, figure of merit is increasing for different dopings. I have studied only for 10 power 19 and 20 dopings because they are significant for semiconductor range. 19 and 20 are important. So, for 19 and 20 you can see that here for p-type the figure of merit is coming out to be more p-type. So, you can say that the material under study is basically p-type dominant, because GT is more, and we have seen that also. For power factor is also coming out to be more for p-type carriers compared to the n-type carrier. So, we can see the figure of merit is higher for p-type for 10 power 19, 10 power 20 it is even more also, we can see that. And what we have done, we have compared our obtained results with the literature, existing literature, and we are getting some comparable values and some are low, and these are from the literature, similar literature, and this is the compound that I have studied, and they are somewhat low. And the low figure of merit values, it is attributed to the higher band gap. The material that we have chosen is having band gap 1.62, but for thermoelectric materials we have to take narrow band gap semiconductors, but we have chosen this one. So, that is why we are getting small band gap, small figure of merit values we are getting. So, finally, I can say that in conclusion, I can say the gentle phase tetragonal compound, it is found to be stable mechanically and dynamically and thermally. Obtained band gap values PBE using PBE and MBJ functionals are 0.74 electron volts, 1.6 electron volts respectively. Band gap using MBJ functional, it is exactly matching with the experimental one. And lattice thermal conductivity, it is estimated using empirical Slack's model, and phono 3 pi also we got. From phono 3 pi we got somewhat lower KL value compared to the Slack's model, and we have explored different types of scattering mechanisms, 3 types, ADP, IMP and POP scattering mechanisms. And among the studied scattering mechanisms, POP scattering is dominating due to the difference between the static and high frequency dielectric constants. And the average mobility also we have studied as a function of temperature, and for n-type carriers it is more because of the lower effective mass of the electrons. And the thermal power S, Seebeck coefficient is also known as thermal power, it is more for n-type, but unfortunately power factor is coming to be higher for the case of p-type carriers because of the higher value of the Seebeck coefficient. And finally, if you come to figure of merit, GT is found more for p-type carriers. So for higher GT you need to get GT up to 2, but we are getting 0.07 something like that only. But if you screen more materials in future with less band gap, you may get 1 or 2 something like that. But as of now we are getting only 0.07 figure of merit, which may be tuned to get higher GT values. And these study results are accepted for publication in Physica Status RDB recently, last week. I acknowledge DST Serb for funding this research through grants EEQ and CRG, and I also acknowledge Kepler facility at ISER Calcutta. I thank my collaborator Bemalang Chatari for giving me computational facility at ISER Calcutta. And this is my research group. Thank you.
Thank you, sir, for a nice lecture. Now session is open for discussion. Any queries?
Actually, there are different kinds of researches. Okay, one part of research is generation of pseudo potentials, and we are not doing that. We use the pseudo potentials given by WASP, because once if you generate pseudo potentials, you have to test that pseudo potentials for different systems. Suppose you have generated a pseudo potential for calcium. For my material, that pseudo potential may work, but for calcium oxide it may not work, because calcium is having a number of structures, right? So you have to test. That is separate research. So we don't generate pseudo potentials. We use pseudo potentials already generated by WASP community. So are you generating or what? Huh? Huh? अच्छा, तो आपने किया ना कभी? Generate I don't do, but mix I do. Yeah. How to do that? Suppose if I am using MBJ functional using WASP. Okay, so there is some parameter alpha and beta, and alpha and beta you have to change. You have to tune to get the desired band gap. So what I do, I submit, I take 0.1, 0.5, 0.7, 1.1. Okay, whatever the band gap is matching, and I will take that one. But not, that is not generation.
Any other question? If there is any query, then let's congratulate Dr. Sango. He has explained all the things from. Thank you, sir, for your talk. So I actually use the DFT for energy optimizing of the superimposed structures. So in my case, we actually synthesize many large structures comprising of many atoms and numbers. For that case, sometimes we could not converge the energy by using DFT. So for that functional basis set, we need to
Changes.
So how to choose the functional basis sets and how to get many occasions we could not get a energy minimized structure. So what does not converge?
Actually, there is no particular method. Suppose if you are working on some particular set of compounds, suppose I am working on some magnetic systems, Okay, so magnetic system, they don't converge. So we have some parameters, A max mix, B mix, B max mix, some parameters are there, you have to change those values. Luckily if you convert, that's fine. So that is why what people do for magnetic system, they don't go for 10 power minus 6 electron volts conversion, they do only for 10 power minus 4, and they report the same also. So that comes through experience. That is the headache that we have.